So thank you for that introduction. I hope I can live up to it. So thank you all for coming out. I know it's been an exhausting and enlightening couple days. So this is the title of my talk. So let me just say a few words about myself. So my background is in pure mathematics. I was doing research in algebraic geometry for a while. After finishing a postdoc at USC about 4.5 years ago, I decided to move to tech industry. It's been great. For the last 2.5 years, I've been working at SignalFX as a data scientist. SignalFX is a real-time analytics platform for monitoring and alerting on infrastructure and application metrics. So I'd like to orient you with a simple example, how we might approach that example, what are some downfalls of that approach, and then develop some more sophisticated statistical methods falling under the umbrella of exponential smoothing to do forecasting and anomaly detection, and then say a little bit about how we might classify time series to tell us what sorts of anomaly detection schemes to use. So we've heard a lot about some of the engineering and organizational and human challenges of monitoring. So I will view monitoring from the statistical viewpoint, and I will completely neglect these other aspects, mainly due to my own lack of expertise and lack of time. So I think you've all heard by now that we need, for various reasons, statistically grounded approaches to monitoring. So environments are much more dynamic than they used to be. We have just a volume and a variety of data that we didn't have just some years ago. Additionally, outages are very expensive, so our statistically grounded approaches should operate in real time. And if you'd like to turn that into a data science problem, this means that we need streaming algorithms for time series. And let me be a little bit more specific. So one requirement is that we should only pass over the data a few times, maybe once. The memory overhead of the computation and the amount of computation required for each incoming point should not depend on the amount of data that we've seen. And finally, our algorithm should be adaptive. So if the patterns and the trends change, then our algorithm should pick up on this and adapt appropriately. Okay, so here's a warm-up example. So maybe I'm walking by a screen and an engineer says, oh, that looks bad, it looks like something changed. Why did my cache hit ratio go up? Can I have an alert when this happens? So if we're tasked with finding an alert for this kind of pattern, we might say, well, it looks like the distribution of values changed at this point. And so we might create two windows, one a baseline period where we sort of learn what's normal, and then another, which is the period we're evaluating for being abnormal. So hopefully they're blue and orange for you as well. And of course, statistics has many tools to allow us to compare two distributions. And so one thing we might do is calculate a range of values based on in the baseline period, for example, using a mean and standard deviation, and say that if a certain percentage of the points in the window being evaluated lie outside, then we declare that the segment is anomalous. So this would amount to comparing a percentile of the orange region to the mean plus or minus 3 standard deviations of the baseline period. And there are other approaches. We could use a t-statistic or a comparison of percentiles, but I just want to zoom in on a particular example just to make things a little bit more concrete. Okay, but the basic idea is that we construct a normal band and compare the current values to that band. So moving a little bit towards engineering, if we actually want to implement this, we might use a rolling window approach. And so this is a schematic of that. So as data arrives, we augment our calculation, and eventually we have enough data to report a baseline or a threshold. And then a new data point arrives, so we have to age out the oldest one and incorporate the newest one. And this keeps happening forever. Okay? And in the previous example, we really have two rolling windows, one for the blue and one for the orange. Okay, and in terms of a template, we might use the following framework. So there's an initialization method, which will declare some quantities with some initial values. And then for a while, we will add points to the calculation. And then eventually, we'll start removing the oldest one and adding the newest one. Okay, so this is sort of a code version of the picture you see on the left. Okay, so let's try to fill this in for some examples. Let's try to make this framework happen. Okay, so everybody's first example, the rolling mean. So to initialize, we declare the count and the sum. When we want to add a point, we have to increment the count and sum appropriately to remove, we decrement, and then someone might say, hey, by the way, what's the mean? And we say, oh, let me assemble that for you. It's the sum divided by the count. And someone might say, well, let's do some higher moments, so you can do the rolling variance as well. There's a very similar approach where you also track the sum of squares and then assemble these quantities into the variance. I have a note on the slide that you should probably use Welford's method for the rolling variance so that no one yells at me if there are some numerical stability people in the audience. No one yelled, so I guess I could have gotten away with it. But anyway, there are some numerical issues with this for some pathological inputs. Okay, so I would like to take the position that rolling windows are a natural foundation for streaming algorithms. So let's think of all of the people who like rolling windows. So engineers like them because there's a small memory overhead, so they can fit lots of jobs on a single instance. And the amount of computation required to add or remove a point is finite. Okay, and this is this concept of incremental-decremental. So maybe I'll say, I learned this term from a paper called Incremental-decremental support vector machines, and there the application was to speed up leave one out cross-validation. So I just wanted to say that I didn't make up this term, and therefore it's real. So designers and engineers also like it. So rolling windows have this nice property that the value of the computation is independent of when you start it. Okay, and so one thing that guarantees is that if you're viewing a chart and then you decide to pan in one direction or the other, the values that you see in a common time period don't change. So there's this nice consistency. Additionally, it makes calculations very easy to reproduce. So someone might be running a calculation on a month of 1 second data, and we don't want to have to grab all of that data and redo the calculation. Instead, if another client is asking for the same result, we're guaranteed to have the same output. And finally, data scientists love rolling windows because they allow us to discard stale data in a principled way. So there are other ways of approaching these problems, but rolling windows have this nice collection of features which make them a natural foundation. Okay, so this is great, except when it's terrible. And so here's another example of a metric, which could be memory or disk. So it looks like it's trending up. And I've also drawn for you the 3 standard deviations band. Doesn't look so promising, so maybe we're not processing any more records, or maybe we ran out of some resource. And of course, this is totally within bounds. It's not so important what I drew to the right. The main thing is that you could draw almost anything, and it would not be declared anomalous by a mean plus or minus 3 standard deviations type approach, or any other variation on this approach. So, oh, yeah, we're dead. Okay, so where are we? So rolling windows are a nice foundation, but it is not enough to just compare distributions. So we need some more developed or more sophisticated methods. And so I'll talk about some ways of modeling, exponential smoothing, and detecting and classifying non-stationary series. And then adapt them to the rolling window framework. And maybe I'll just remark here, if you're inviting billions of data points to a dinner party, some are going to get lost and some are going to show up late, and you probably have to exclude them from the calculation, so they'll show up as null. So all of these methods have been made to handle nulls. This is actually quite painful, but for simplicity, I'll just assume that all of the data is there in this talk. Okay, so let's move on to another approach, exponential smoothing. Okay, so a way of viewing this example that doesn't make reference to statistics is, well, we have some baseline period during which we construct a forecast and have an idea of the error in that forecast, and then we can declare that the orange segment is anomalous because our forecast has become hilariously wrong. Okay, and in the case where the signal is mostly stationary, it actually makes sense to use the mean as the forecast and the standard deviation as the error. But in our more interesting example, and to be honest, it's not even that interesting, it's just a line, the mean is quite a poor forecast. So let's try to improve on that. So one way to make progress is to use an exponentially weighted moving average. And the main idea is that more recent data are more relevant in calculating a baseline. So the mean weights all points equally. Maybe we should try to break that assumption. So we initialize the value of the smooth series, which I'll call S, at the first value we saw. And then afterwards, our new value of the smooth series will be a convex combination of the data point that just arrived and our previous value for the smooth series. And here alpha is a number between 0 and 1, which is a smoothing parameter, which is qualitatively very similar to a window length. Okay, and if you look at this example, the exponentially weighted moving average series lags less than the usual average does, and the forecast is therefore more accurate. So what I have in this picture is the rolling average with the window specified in the bottom left in green, and then the exponentially weighted moving average in black. And then if you were to start a forecast at the period where the blue input signal goes flat, you would get those dashed lines. Okay, so that's a little bit better. If you look at this formula, I wasn't supposed to go back, you may notice that the point x0 is always part of the calculation. Okay, a point never ages out. Its weight just decays. So how can we make a rolling window variation? Well, if you stare at these formulas, you may notice that every value of the exponentially smooth series is a convex combination of points that we've seen so far. And you may also notice that the ratio of the weights between 2 points is always 1 minus alpha. And so just as the mean can be constructed as a sum divided by a count, we can just make things a little bit fuzzy and say, oh, let's have a weighted sum divided by a weighted count. So I just explicitly downgrade a point according to its age in the window. Okay, and then once you've seen the rolling window implementation in this prime and stream framework for the moving average, it's fairly straightforward to develop one for the exponentially weighted moving average. So our initialization basically declares these two quantities, and then when we add a point, we need to shift everything over, age it by 1. That's what the multiplication by c does. And then we need to insert the newest point, and that's what adding 1 or x does. And then removal just consists of getting rid of the oldest summand. Okay, and then if someone asks for the exponentially weighted moving average, we just assemble the ratio as before. Okay, so that's a rolling window variation on the exponentially weighted moving average. So that's okay. I would say we're not quite done yet. One thing that the exponentially weighted moving average doesn't know about is the trend of the series. So let's model that as well. So, if you have single, why not double? So double exponential smoothing models two quantities, namely the level, which we'll still call S, and the trend, which we'll call B. And now we initialize them in a similar way. So the first value of the level is x1, and the first value of the trend is x1 minus x0. And now we have a similar update rule for later data points. So now our current estimate, for our current estimate of the level, we take the previous value of the level, the previous value of the trend, add them together, and then make a convex combination with the data point that just arrived. And then for the trend, we take into account the successive differences of the levels, and then also incorporate the previous estimate of the trend. Okay, and now alpha and beta are smoothing parameters as before. Okay. One nice thing about this approach is that we can form an explicit forecast into the future just by multiplying the trend term by some number and then adding our current estimate of the level to it. Okay, and here are some references. As you can see, can you read it? Well, anyway, it's 1956 and 1957. So far there's nothing new, but it's coming. So let me try to get you excited. So of course, the double exponentially weighted moving average just totally crushes it. It's during the baseline period, it's tracking very nicely. The forecasts are correct. The forecast error is much smaller during the baseline period, and the errors are due to noise, not to a misspecified model, as we saw with the other two lines. the anomaly is correctly labeled, so all of a sudden our forecast, if you look at the right-hand side of the graph, is laughably wrong. So that looks like an anomaly. And we have the ability to alert when, for example, the 24-hour ahead forecast is some value that we care about. So we're going to run out of disk in a day. All right. So that's great. So again, there's this problem that the computation depends on all of the historical data, and we'd like a version that only depends on a rolling window. So if you only store and update the level and trend, how do you remove the influence of the oldest point on the current values? And the idea is to store some additional state, which basically tracks the influence of the initial terms, S1 and B1, on the current terms, Sn and Bn. Call these influence terms. And so the addition step consists of the usual update rules, which you saw a couple slides ago, plus the care and feeding for the influence terms. And then removal is similarly more involved. So we have to update all of the terms appropriately. But the punchline is that we only need access to the endpoints of the window, much like we do for a rolling mean. The amount of computation has no dependence on the window size, and the memory overhead is also fixed. Okay, so we can achieve all of the desired properties of this incremental-decremental framework by keeping track of this additional state. And let me shine some light on some of the dark statistical corners that arise. To solve this problem, I found it very helpful to view double exponential smoothing as a weighted, directed acyclic graph. And the dictionary for going between the two is that vertices are labeled by quantities they represent. An edge weight represents multiplication by some scale or value. And if you have multiple incoming edges, then you add them up. Okay, and if you like formulas, then this is probably a nicer way to say it. The value at some vertex is the sum over incoming edges of the weight of that edge times the quantity sitting at the source of that edge. Okay, and if you stare at one of these nodes for long enough and compare it to the formulas from before, you'll see they agree. Maybe don't do it now. I'll put the slides in the Slack channel and let me know if there are any mistakes. So now, how does this help us do the removal? Well, we can think of removing the influence of the initial points as an operation on this graph. So basically what we'd like to do is cut away the part that's in degree 0 and degree 1, and then glue that x1 value in where b2 is, and change the weights in the degree 2 column. Okay, so we want to modify this graph in some way. So I'll give a sketch of how this works. I've written this up, and it's been accepted for publication, so you can also look there, but I'll try to explain the main idea in the next few slides via some beautiful animation. So, So the first thing we do is we cut away the nodes corresponding to x0 and x1. And to do this, we exploit the linearity of Sn and Bn in those initial values, S1 and B1. So if we know how, for example, B1 affects Sn, and we know x0 points to B1 with weight -1, then we just need to update Sn by plus x0 times the influence of B1 on Sn. Okay, and there are a handful of other update rules, but they follow the same basic logic. So we exploit these influence terms and value, and we understand how the initial data points enter this graph. Okay, so we cut away x0 and x1, so that's good. We're feeling better. And then we need to also replace the influence of S1 and B1 with the influence of S2 and B2, because the next time we try to do an update, the initial, the oldest points in the window will have index 2 or degree 2. And so to do that, we can express the influence of S1 as a linear combination of influences over outgoing edges, and similarly for B1. And if you write this all down, you get a system of linear equations. There are 2 equations and 2 unknowns, and you know how to do this, so we can solve and then update the influence terms accordingly. Okay, so now we can pretend that the degree 0 and degree 1 part of the graph aren't there. And then we need to just do a little bit of housekeeping in degree 2. And to do that, we have to just glue in x1, make it point to b2 with weight -1, and also change the weights in the second column. And that's accomplished along the same lines as the cutting procedure. So we basically cut away some part of the graph, update our influence terms, and glue something back in. Okay, so that's more or less how it works. To actually write it down in code is somewhat involved, but this is the key idea. And so if you track this additional state, you can do a rolling windows version of double exponential smoothing. Okay. So I always hope someone will see this and make some connection, and we can write some paper together. But maybe that will happen later. Okay, so let's move on to classification. So there are lots of anomaly detection schemes out there. How do we know which one is appropriate for our time series? Okay, so there's a fundamental concept in time series modeling is stationarity. And stationarity means that the distribution of values doesn't change over time. Okay, I'll focus on something a little bit more narrow, which is a level stationarity statistic called the KPSS statistic. And this tests the hypothesis that a time series is stationary around its mean. So larger values of the statistic are more evidence for rejecting the hypothesis of stationarity. And here's another reference. This is from 1992. So this came from econometrics. It was originally applied to basic economic data, so they didn't know about monitoring. But we can still use this statistic. So there's a model and a definition. So the model is that the time series is the sum of a random walk plus some noise. And then the statistic is testing the hypothesis that the variance of the U term, which makes the random walk go or not, is 0. And of course, if it's 0, then the series is stationary about this common value, R0 through Rn. And so here's the definition. Let mu denote the mean of the series as usual. Okay, now form the residuals against the mean. So just subtract it from all of the data points in the window. Call those the EIs. Now form their partial sums. Now square those, add them all up, put that in the numerator, and divide by some normalization term. Okay, so that's the definition of the statistic. So before we get into anything else, why do you care about this? So here are two signals with qualitatively different behaviors. So on the magenta person on the left there, looks like it's mostly stationary. Maybe it experiences a small step change, and then it starts to trend up. But for the most part, it's more or less stationary. Whereas the fellow on the right, the blue, has a very strong seasonality. So for both of these, we have about a week of data, maybe a little less. And now let me plot for you the distribution of the 1-hour KPSS statistics for these two signals. So this is the interquartile range, the 25th to 75th percentiles of the KPSS statistics. So there's a fairly clean separation between the magenta person and the blue one. And sitting in between them is the value of the statistic associated with the p-value of 2.5%. So this is some step towards classifying time series as stationary or not. So a concrete application is, well, these mean plus or minus 3 standard deviation and friends alerts are appropriate for signals which look like the magenta one. And so if we can stream the KPSS statistic, then we can choose dynamically whether or not to use this type of alerting strategy or to use something else. And more generally, there's an approach to time series modeling called Box-Jenkins, where we try to make our series stationary by a series of transformations. So for example, we might apply seasonal differencing to the blue person and expect that if we subtract last week's values, the result should be somewhat stationary. So we can, in real time, in a streaming fashion, evaluate various modeling choices, provided we have access to the KPSS statistic. Okay. So let me say a few words about how this works. Again, going to some dark corners. So we're trying to calculate the statistic on rolling windows. So it's not so nice because the mean of the window changes, and so the residuals and their partial sums and the squares of those change as well. And so the solution is to just do some algebra. So I'll show you an example. I understand it's not so easy to follow this on a slide in real time, but you can stare at this later. And maybe just for some orientation, what we're doing is decomposing something we care about as an easy-to-evaluate function of terms which are algebraically simpler than the one we started with. So hopefully, like in the case of the variance, we can just do this in one step, but it doesn't always work that way, and so sometimes we need to do another level where we try to increment the quantities that appear in the function f, and we see what terms arise, and similarly for the decrementing. So there's this kind of nested algebra which needs to be tracked. So I'll show you one example. So in the level stationarity statistic, this is the expression for the ith partial sum. And if you square it, you get some term which is quadratic in the mean. And then if you sum those, you get something which is, again, quadratic in the mean. The coefficients are just a little bit nastier. Okay, so I will focus mostly on the last one, the one on the right, the sum of squared counts. I mean, you have to do all of them to make this work. And when you look at the rules for decrementing, you realize, oh, I need to track some other things as well, so you have to store those. And you also need the count and the sum. But let me just explain briefly how it works for one of these quantities. So this is the sum of squared counts. So the required update is basically throwing away the initial point and re-indexing. And so if we throw in the I equals 1 term to this I minus 1 squared expression, that would be 0, so we can add it there. And then when we expand this, the first term that appears on the left-hand side is the old value. So then when we rearrange, we see that the old value of this expression minus the new value is twice something we were tracking minus 1 time something else we were tracking. And so during the removal method, we have to decrement the sum of squared counts by twice sum of counts minus count. So maybe the details are not so important, but the organizing algebra is moderately interesting. Okay, so I think I'm pretty much out of time. I just wanted to briefly mention that there's also a trend stationarity variant where you detect whether something is stationary around a linear trend line, which is useful, for example, to tell whether or not you're in this situation where we were increasing and then all of a sudden we went flat. So you just add another term to the model. And then in the definition, instead of residuals against the mean, you use residuals against a regression line. It's a generalization. And again, the complication is that the linear regression solution is changing as the data is arriving. And so everything else is changing. You need to track all of this. So you need an incremental-decremental expression for the solution to the regression problem, which is possible, and again some more algebra, which I don't have on slides, but you can do this for the trend stationarity version as well. And so the main thing I want to conclude with is that we can produce high-quality thresholds, high-quality alerts by using time series processing algorithms that can operate in real time by computing some of these more interesting statistics in an incremental-decremental way. Okay, thank you.
Any questions? The front row?
Could you say the second question again? So the first question was if it's in production. The answer is yes. The second question was? The second question depends on the type of the signal. You need to apply different models, right? Yes. So it means that you need to tune it up for every metric or for every parameter or how it works. Okay, so the question is whether, I guess, you need to be a data scientist in order to use this. So I would say if you are a data scientist, this is a tool and you're trying to do stream processing. This is yet another tool that will make your life easier, but it is not necessary that you be a data scientist. So maybe someone will just package for you an alerting algorithm that takes into account the value of the KPSS statistic, for example, and chooses the appropriate algorithm, or takes into account the level stationarity, trend stationarity, maybe some seasonalities, and adjusts the threshold based on that. So it is a tool. But it can also, it is not it is not so difficult to package it up into something which is consumable by an engineer.
Back there on the left.
So the question is whether I've tried to use recurrent neural networks. I've played around with online versions of random forests and also some recurrent neural networks. Based on some investigations, I did not feel it was worth investing so many resources in these projects. But if there are some examples where these more complex models are needed, I would be happy to consider them. At the moment, I didn't see a tremendous additional value from these methods, which are more difficult to maintain and operate, and also more difficult to implement. So the question is, what window sizes have we found effective? I've developed some heuristics, and these basically appear as default values. But there is a general problem that any of these algorithms does have a dependence on the window size. So, for example, if you take this weekly seasonal signal and calculate stationarity over a long enough window, eventually it looks stationary. Okay, so there's still some amount of domain knowledge that needs to be incorporated, but generally we have some idea that things will vary with some weekly pattern or some daily pattern, and we want to distinguish those from the things that are mostly flat or have some trend. So there's a very wild universe of possible time series that we might see, and we probably can't handle all of them, but we have some idea of the types of data that we might see, and so we can incorporate those heuristics into default values and the types of models that we expose.
Anyone else? Okay, great. Thank you very much, Joe. Should we start setting up?